Good day and welcome to Letters and Politics. I'm Mitch Jeserich. Today we're going to be in conversation about the history of trying to come up with a single theory that explains the laws of the universe, from the great debates of Democritus and Pythagoras to Einstein to the present day. And we're very fortunate to be able to do it with a renowned theoretical physicist who's trying to come up with such a theory himself, Michio Kaku. Michio Kaku is a professor of physics at the City University of New York. He's co-founder of the string field theory, and he's also the author of a number of books. His latest is called The God Equation, The Quest for a Theory of Everything. He joins us via Zoom. Michio Kaku, it is my very good pleasure to welcome you back to this program.
Glad to be on the show.
And I should also add, you have a long history with this radio network, the Pacifica Radio Network. You've hosted for many years now the show Explorations. And also thinking about your background in activism. You also have a long history in activism, anti-war, anti-nuclear activism. So I see you, and I think a lot of our listeners see you as an old friend. So I hope you wouldn't mind if I start on the personal by just asking,
Sure.
how are you? And how have you been in the pandemic?
Well, I'm reminded of what happened to another physicist back in the year 1666. There was the Great Plague that hit London. 1/4 of the population of London died as a consequence of that horrible Black Plague. One 23-year-old physicist was sent home. Cambridge University was shut down. It was locked down. And he was strolling on his estate and he saw an apple fall. He saw an apple fall, then he looked at the moon, and then he said, "Does the moon also fall?" And then he realized that he didn't have the mathematics to calculate the falling moon. So he created it. It's called calculus. Well, that 23-year-old man was Isaac Newton. So what came out of the pandemic of 1666 is one of the greatest theories of all time, the theory of mechanics and gravity, which gave us the Industrial Revolution. Every steam engine, every machine that came out of the machine age owes its lineage to Newton's laws of motion. So you see, pandemics are not totally bad. Out of the pandemic of 1666 came the Industrial Revolution.
And so did you get any insight during this pandemic? Did it give you any downtime to be able to kind of think about string theory and getting to a single theory?
Well, let me tell you how I got into the game and what I'm doing now. When I was 8 years old, something happened which changed my life completely. My whole destiny veered off in a different direction when I was 8 years old. A great scientist had just died, and all the newspapers flashed a picture of his desk, just his desk. And on the desk was this unfinished book. And the caption said, "The greatest scientist of our time could not finish that book." So I said to myself, wow, what's so hard that a great man could not finish it? It's a homework problem. He could ask his mother. I mean, what's the big deal? So I went to the library and I found out that this man's name was Albert Einstein. And that book was to be the theory of everything, the God equation, an equation no more than 1 inch long that would allow him to, quote, read the mind of God. Well, I was hooked. I had to know everything about this man and what he did. So when I was in high school, I decided to be part of this revolution. So I decided to build an atom smasher, a 2.3 million electron volt betatron particle accelerator. I went to my mom and I said, "Mom, can I build a particle accelerator in the garage?" And she said, "Sure. And don't forget to take out the garbage." Well, I took out the garbage. I assembled 400 pounds of transformer steel, 22 miles of copper wire, and I built a 6 kilowatt, 2 million electron volt betatron particle accelerator in the garage. Every time I plugged it in, I would blow out all the circuit breakers in the house. The whole house would be plunged in darkness. And my poor mom would come home and say, "Where's the fuse? And why couldn't I have a son who plays basketball? Maybe if I buy him a baseball. And for God's sake, why can't he find a nice Japanese girlfriend?" Well, because of this science fair project, I went to the National Science Fair and I met a physicist, Edward Teller, the father of the hydrogen bomb. And he took me under his wing. He immediately knew what I was doing. I didn't have to explain to Edward Teller what a particle accelerator was, what antimatter was. He knew exactly what I was doing. So he offered me a scholarship to Harvard. So when I graduated from Harvard, it was time to go to grad school. I interviewed with Edward Teller, and he offered me a job to design hydrogen warheads. He offered me a job to work at Livermore or Los Alamos National Laboratory or MIT designing hydrogen warheads. Well, I respectfully declined the offer because I wanted to work on something bigger, even bigger than a hydrogen bomb. I wanted to work on the Big Bang. I wanted to work on the creation of the universe, a theory of everything. But then again, sometimes fate gives you a curveball.
The story about Edward Teller is interesting because again, you would become active in the anti-nuclear movement. Did you have a split with Edward Teller?
Well, Edward Teller was all in favor of nuclear power this, nuclear power that. But when it came to commercial nuclear power, he was a physicist. He knew that it was a Faustian bargain. Unlimited power, the power of the devil. The price, your soul. And so Edward Teller had a very famous statement. He said, nuclear power plants do not belong on the surface of the earth. They belong underground. Because if there's a meltdown, all you have to do is put the lid on it and walk away from the meltdown. So he was a physicist. He said, yes, nuclear is the way to go, but not commercial nuclear power on the face of the earth. Underground, he said.
Yeah. What would that mean to have it underground? And if there was a disaster, I mean, is it that easy just to put a lid on top of it?
Look at Chernobyl. Back in 1986, the lid of that reactor blew off, and about 20% of the core was vaporized and shot into outer space, shot into the area over Kiev, and eventually into Western Europe. Think about that. If that accident had happened underground, all you would have to do is just put the manhole cover on it and walk away. Or look at Fukushima. 3 nuclear power plants went berserk, melted down. We now know the cores are totally liquefied. We've never seen this before, totally liquefied uranium core for 3 nuclear power plants. I was asked by ABC News, what do you do with 3 runaway nuclear power plants? And I said, we should do what we did to Chernobyl, sandbag it. Gorbachev called in the Red Air Force. The Red Air Force sandbagged that flaming reactor accident, dumped borated water on it and sand, and sealed the whole thing in concrete. It's a tomb, what's left of the Chernobyl nuclear power plant. They should have done that in Japan, because now we have this raging accident that's still out of control, waste water building up, millions of gallons of wastewater. And what are they going to do with it? Eventually dump it into the ocean. And some people don't like that at all.
What could that mean?
The problem is that these products, cesium, radioactive cesium-137, iodine-131, strontium-90, they occur in water-soluble form. After a nuclear accident, sometimes it rains, and that nuclear material gets washed into the soil. That's what we see at Chernobyl. That's what we see at Fukushima. And all this water is just accumulating on site, millions of gallons of water, because the loop is open. They couldn't close the loop on cooling water. Cooling water usually flows in a loop. It's finite. However, the loop is broken. They can't fix it. They're trying to use robots to fix that loop. So it's bleeding. Still today, it is bleeding. And so what do they do with that water? They try to freeze some of it, dam some of it, but eventually dump it in the ocean.
And then I guess that brings up a whole host of questions of what happens to the ocean and marine life. Let me try to get us back on topic. of
Hmm.
today's conversation concerning the theory of everything. How important is our knowledge in the nuclear sciences when it comes to trying to come up with a theory for everything?
Well, every time we worked out a force, it changed world history. When Isaac Newton worked out the force of gravity, that gave us mechanics. That in turn allows us to make machines, steam engines that powered the Industrial Revolution. And then about 150 years ago, Maxwell worked out the laws of electricity and magnetism. That lit up our cities. All of a sudden, we had dynamos, generators. All of a sudden, we had vacuum cleaners. So that changed world history. And then Einstein wrote down E equals mc squared. Excuse me. That helped to work out the nuclear force. And so every time we unleash an equation describing a force, we change world history. Now we're talking about a theory of everything, a theory of all four forces in one equation, perhaps no more than 1 inch long, like E equals mc squared. That equation is also half an inch long, and that gave us the nuclear age. It told us how the sun shines and why the stars twinkle. So the theory of everything would be a theory of the entire universe. It would answer questions that have haunted philosophers and physicists for thousands of years. For example, is time travel possible? Are there other universes, parallel universes? Are there other dimensions? What happened before the Big Bang? Is there a white hole on the other end of a black hole? You see, none of these questions are answerable with today's physics. We need a theory of everything to explain to us how the universe works. I mean, think of it. What happened before the Big Bang? We're clueless at the present time. But string theory, which is what I work on, actually gives us a clue, an answer, perhaps, to all these cosmic questions.
What keeps us from getting to a theory of everything? Now, I guess we have four forces: gravity, electromagnetic, strong and weak nuclear forces. Is it that these forces in themselves we understand or we have a good understanding of them, but trying to combine them, trying to get them to see where they fit with each other has been elusive?
It's all a question of mathematics. When you want to learn, for example, French civilization, you learn about the Eiffel Tower and you tour the sites, but eventually you got to pay your dues. You got to learn the French language. You got to conjugate verbs. You got to be able to speak the language of the people. Well, the language of Mother Nature is mathematics. And so we can learn about black holes and big bangs from a point of view of a children's book. But to actually get into the guts of these things, you do need mathematics. And unfortunately, the mathematics is so high, it's so advanced that only a rarefied few people, maybe a few hundred, can understand it. So we're a part of a small club trying to figure out how to put all these equations together. Now, let's say one of your listeners right now is inspired by this program to complete the theory of everything and write God's equation. What should you do? Well, I suggest you first tell me first. And we can split the Nobel Prize money, you and me, and be noticed as the next Einsteins. So you see, there's still hope. We don't yet have the God equation. We have a theory, string theory, but it's not in its final form. And when it does go into its final form, then we can test it. And then we can answer these questions. What happened before the Big Bang? Is there a white hole on the other side of a black hole? What does it all mean? What is the final theory? That's the goal.
Einstein tried to get to this God equation and
Mm-hmm.
wasn't able to. You spent, as you indicated earlier, a lot of time diving into his work. Where did he run into difficulty?
Well, you see, he worked on it from 1925 to 1955. 30 years of his life, he chased after it. But the nuclear force was this missing piece of the jigsaw puzzle. You're trying to put together this jigsaw puzzle with a huge chunk missing, and that's the nuclear force. I mean, think of it. In 1925, we didn't know beans about the nuclear force. And here's Einstein trying to unify everything into a single equation with a missing piece of the jigsaw puzzle. Well, today we have that piece, and we know that what came out of that piece is strings. Every time we try to put quarks together, strings occur that glue them together. And so now we have a new paradigm to look at subatomic particles. And that paradigm is through strings and music. You know, after World War II, we started to smash protons apart. And what did we find? A simple, elegant, beautiful theory? No, hundreds of subatomic particles. J. Robert Oppenheimer, father of the atomic bomb, was so frustrated that this zoo of particles was emerging that he said, quote, "The Nobel Prize in Physics should go to the physicist who does not discover a new particle this year." Well, today we think that the only paradigm rich enough to explain these hundreds of particles is music. Music is rich enough to explain all these particles. So if I had a super microscope, I could peer into an electron. It would not be a dot. Every textbook says that an electron is a dot. We would actually see that it's a rubber band. You twang it, it changes frequency. It turns into a neutrino. You twang it again, turns into a quark. In other words, how many notes can you make on a rubber band? Infinite number. So how many particles you get? An infinite number of particles, all from a rubber band. And so physics becomes the harmonies you can make on rubber bands, with each vibration being a particle. Chemistry is the melodies you can play on these rubber bands as they bump into each other. The universe is a symphony of strings. And then the mind of God that Einstein spent so many decades chasing after, is cosmic music resonating through hyperspace. That is the mind of God.
And that string theory that you're outlining about the rubber band, this won't nearly be as good of an example, but it made me think of going to a park and seeing that person who is able to turn a balloon into all kinds of different animals. I mean, I guess we could say, there are an infinite amount of animals or objects you could turn a balloon into.
Exactly the same. In fact, we now realize that strings coexist with membranes or balloons, and you're exactly right. The number of ways we can twist a balloon corresponds to the number of ways we can twist a membrane, which in turn corresponds to particles. That's why we have so many goddamn subatomic particles. When I got my PhD from Berkeley so many decades ago, I had to memorize the names of these hundreds of subatomic particles. Goddamn subatomic particles, we were drowning in them. In the future, I hope that when you get your PhD from Berkeley, all you would have to do is say string theory and get your PhD.
You mentioned music, and I immediately, as I oftentimes do, think about sort of the ancient world. This is what Pythagoras was talking about, or music anyways.
That's right.
Well, Pythagoras was talking about music, yeah.
There were two great theories coming out of ancient Greece, two great theories. Democritus talked about atoms. A means cannot, tum means cut. So atom means that which cannot be cut. But Pythagoras comes along and says, no. It's music. Music is the only paradigm rich enough to explain the vast diversity of the world. How do you do it? Well, he looked at a lyre string. He plucked a lyre string, and he realized that the longer the string, the lower the note. And then he went to a blacksmith shop, and when you pound steel, the longer the bar, the lower the note. So he said, aha, mathematics. This is the mathematics of resonances. And so he wrote down, for the first time in human history, the laws of music. All the laws of music were worked out by Pythagoras back then. And then he made the stunning statement, not just music, but the universe. The universe consists of musical notes and harmonies and melodies. But it never went anywhere. He had a school, by the way, a school devoted to this idea, but it never went anywhere because, of course, we had to figure out the laws of chemistry. Well, now we realize that all of biology can be summarized in terms of chemistry. All of chemistry can be summarized in terms of physics. And all of physics, in turn, can be summarized by two theories, the big and the small. The big is relativity, the theory of the Big Bang, black holes, and the theory of the small, transistors, lasers, particles. This conversation is made possible by the quantum theory. Now, the problem is, it's like God having a left hand and a right hand that don't talk to each other. These two theories, the left hand and the right hand of God, don't like each other. They're based on different mathematics, they're different principles, and our job is to unify relativity with the quantum theory. That's the whole ball of wax. That's the holy grail. And again, if you figure this out, tell me first.
Where is that line between the two? And what happens when you get there?
Well, we don't know, but we'll be able to answer some of the deepest questions of the universe. For example, our universe is dying. This is the second law of thermodynamics. In a closed system, everything rusts, decays, falls apart, and dies. That's why we die, by the way. We die because we build up errors in our DNA. These errors build up, cells get sluggish, and eventually die. That's why we die. That's how the universe will also die. The universe will get cold, very cold. Nothing but a collection of black holes, neutron stars, and dead planets. But there's one way out of the death of everything. One and only one way to escape the death of everything. And that is to leave our universe, to enter a wormhole, a gateway, a passageway, a subway tunnel, out of our universe to another universe, which is warmer and more receptive. And then we have another universe to mess up. We'll have two universes to mess up instead of one. So physics is not necessarily a death warrant. There's an escape hatch, and that is wormholes. Now, you've seen wormholes all your life. When you see Alice in Wonderland, the looking glass is the wormhole. And who first proposed wormholes? Einstein himself, back in 1935, wrote a paper with his student, Nathan Rosen, and today they're called Einstein-Rosen bridges. Einstein-Rosen bridges are connections between universes. So in other words, out of Einstein's theory, we now believe that our universe is a bubble. We live on the skin of the bubble. The bubble's expanding. That's called the Big Bang theory. But string theory says there are other bubbles out there. Other bubble in a bubble bath of universes. And when we collide with another bubble, that's the Big Bang. The Big Bang is either the collision of universes or the fissioning of universes. And this is what the universe is expanding into. You know, children ask that question. At a science museum, they say, Mommy, Daddy, if the universe is expanding, what is it expanding into? Well, it's expanding into another dimension. Our universe is three-dimensional, but there are other dimensions out there. In fact, string theory says there's probably 10 or 11 dimensions out there.
This is Letters and Politics, and we are in conversation with Michio Kaku, professor of physics at City University of New York, co-founder of String Field Theory, and the author of a number of books. He joins us for a conversation on his latest book. It's called The God Equation, The Quest for a Theory of Everything. Michio Kaku on Friday will also be participating in a local Bay Area event, but because of the pandemic, anyone, anywhere in the world could probably also participate with the San Francisco Commonwealth Club on Friday. And if you're interested in that and want to observe it, you could find out the details of how to do that at the San Francisco Commonwealth website. It's interesting thinking about these multiple universes. And I heard you explain in a different interview that what would happen if we were to travel back in time? And I think the example you gave is, what if I traveled back to the Civil War era, 1865, and prevented the assassination of Abraham Lincoln? In my own world, in my own universe, that would not bring Abraham Lincoln back to life. What had happened had happened. But that would have, in some ways, you explained, would have created a different river in a different universe in which Lincoln would still be alive and was not assassinated.
Yes. Einstein gives us a picture that time is a river. Newton thought that time was like an arrow. You fire it, it goes in one direction, never comes back. Einstein says not so fast. Stars, galaxies can warp time, so time can speed up and slow down. The new wrinkle coming from string theory is that the river of time can fork into two rivers or have a whirlpool, whirlpools in the fabric of a river of time. And if it forks into two rivers, then you can resolve all the paradoxes of time travel. The big paradox is, if you go back in time and meet yourself as a child and kill yourself, how can you be alive if you just killed yourself as a child in the past? Well, when you go between rivers, you go between different universes. In one universe, Abraham Lincoln was assassinated. That's your universe. That's your past. That's your timeline. But in this other universe, Abraham Lincoln was saved and lived after the Civil War. But that Abraham Lincoln is not yours. It's another universe's Abraham Lincoln. Now, to me, I find this very pleasing because you see, when I was a child, I knew that my parents were Buddhists. And in Buddhism, there's no beginning or end. There's just nirvana. But I was raised as a Presbyterian. So in the Presbyterian church, there is a beginning of the universe. God says, let there be light, and the universe gets started. So either the universe had a beginning or it didn't. Which is it? Well, now with this new theory, the multiverse idea of string theory, you can meld these two diametrically opposed theories together. You see, our universe had a beginning. Our universe did have a Big Bang. But Big Bangs are happening all the time. There's a bubble bath of these universes floating in hyperspace. In some of these universes, well, Abraham Lincoln lived on. And then the next question is Elvis Presley still alive in a parallel universe? And the answer is probably yes. There's probably a universe where Elvis Presley, the king, is still belting out hits, even today, because in that universe, he never died. Now, this sounds bizarre. This sounds crazy, but it's called quantum mechanics. The quantum world has electrons doing this all the time. Electrons can be two places at once. Electrons can disappear, reappear someplace else. That's called transistors, lasers, the internet revolution, digital computers. They all rest on the idea that electricity is not what you think it is. Electrons can disappear, reappear, be two places at the same time. So if electrons can do it, why not universes? And that's where quantum universes come into the picture. And that's why we're forced to go into this direction if you want a unified theory.
You'll forgive me for coming back to the personal, but my interest was piqued when you indicated your parents were Buddhist, but you were raised Presbyterian. How did that happen? And I mean, you're from San Jose, right, or the Bay Area?
First of all, I was born in San Jose, which is the heart of Silicon Valley. But back then, it was all apple orchards, trees. I used to play with the alfalfa fields, play in the trees until it became Silicon Valley. And I went to school in Palo Alto. But during the war, during World War II, my parents were locked up between 1942 and 1946. They were placed behind barbed wire and armed guards. They were warned that the guards had orders to shoot to kill if they ever tried to leave the relocation camp. But after the war was over, that's when things began to slowly settle back down to normal. And that's why I wanted to do something ambitious. And that's why when I was a kid, I decided to follow in the footsteps of Albert Einstein, build my own particle accelerator. But I learned something from my parents. And that is because of being locked up for so many years, having your assets confiscated, having all your rights taken away. First of all, you have to make sure it doesn't happen again. Fight to make sure that this does not happen again, that this stain on American history is never repeated. But of course, don't have a chip on your shoulder. go with the flow, do something, make something of yourself, but always keep in mind the fact that when times are bad, people reach for a scapegoat. And that's dangerous because people want to blame other people for problems of which they had no inkling of what happened. And so the point here is that you have to fight it all the way if these forces of ignorance start to rise.
Thinking about the internment of your parents during World War II, does that make you think about what we're seeing today, the harassment and violent acts against Asian Americans during the pandemic?
If you get a graph paper and you plot on one graph the economy and also the psychological anxiety of the population, so economic and political anxiety on one hand, and on the other hand, the incidence of various racist attacks, you realize there's a correlation. And when times are bad, people want to blame somebody for it. Okay. And people become irrational. People that may be normally quite rational jump on the bandwagon if they see bad times, if they want to blame somebody for it, and they want a scapegoat. And that's something that we have to fight constantly. And right now, the economy is getting a little bit better. So maybe there's a glimmer of hope there. But the point is that wherever it happens, you have to fight it.
Yeah. Pythagoras and music. But was this the early beginnings of string theory, do you think? Is there a strong connection there?
Well, philosophically, I think yes, that there were two paradigms to explain the universe. One is the atomic theory. Everything's made out of tiny little billiard balls called atoms. But that doesn't explain why we have so many different kinds of matter. Why do we have stars, galaxies, planets, bacteria, viruses, people? Why do we have all these things? Music, of course, is infinite. Of course, you have an infinite number of forms of music depending upon what note you're looking at, what harmony you're looking at. And that's where string theory owes its philosophical origins, back to Pythagoras. Now, the people who invented string theory were looking at the nuclear force. Out of the nuclear force came strings that make quarks, that bind quarks together. Why do quarks bind together to form a proton? It's like a little string that binds them together. So that's where the idea of strings came from. It came from the nuclear force. But we realized, looking at history, that Pythagoras was there 2,000 years ago, way ahead of us.
Yeah. And today with string theory, it's still a theory. What is it? You need the math to be able to ultimately prove this theory, and just haven't gotten there yet?
Well, as Carl Sagan once said, remarkable claims require remarkable proof. Now, 2 weeks ago, stunning news came out of Fermilab outside Chicago and the Large Hadron Collider outside Geneva, Switzerland. We have a theory of almost everything. It's called the Standard Model. It describes the quantum theory of particles. It does a great job, but it has a problem. It does not mention gravity, and it is ugly as sin. It has 36 quarks and antiquarks, 20 free parameters that you can adjust, 3 generations of subatomic particles. It's a mess, but it works. You can't dispute that. So we think that it's nothing but the first level of the vibrating string, but there are higher octaves. Well, 2 weeks ago, for the first time in 50 years, we found a crack in the Standard Model. In other words, there's a higher theory out there, a new theory lurking, which hopefully is beautiful, unlike the Standard Model of today. Now, when I think of the Standard Model, I think of getting Scotch tape and getting an aardvark, a platypus, and a whale, and Scotch taping them together and calling that nature's finest evolutionary creation, the end product of millions of years of elegant evolution at work. That's a Standard Model. It is ugly as sin. So no one thinks it's the theory of everything, but it could be the clue, an experimental clue to the theory of everything.
Because the standard model, despite its unpleasing aspects, actually works.
It fits the low energy data. But now, looking at higher energies, we find a deviation. That could be a signal of a higher theory, which is symmetrical, which is beautiful, like string theory. That's the hope, anyway.
And you're thinking the standard model might be just the tip of the iceberg, or a small portion of a larger explanation?
That's right. Einstein once said that if you see the tail of a lion, you can pretty much bet that there may be a lion at the other end. So this could be like the tail of a lion. The first crack in the standard model of particles in 50 years. This is big news. To me. Now, there's other theories other ways you can test the theory. The universe is not mainly made of atoms. Every high school textbook is wrong. The universe is made out of dark matter. The matter of the universe is invisible, like dark matter. And we're clueless as to what dark matter is. It holds the galaxy together, makes up most of the universe. We think dark matter could be the next octave of the string. So if so, by teasing apart the mysteries of dark matter in the laboratory, we may be able to prove or disprove this theory.
I'm really interested in Ptolemy's Almagest. This is dating back to the ancient world. This is Alexandria, Egypt. And Ptolemy puts out a model of the world. I guess we call it a geocentric model, in which the Earth is the center of the universe and everything revolves around the Earth. And we know, I'm not interested because I think it's right. We know it's not right. But what has always fascinated me about Ptolemy's Almagest is that still, for its day, it worked, meaning it helped. Because of it, you knew when to plant the seeds. You knew how to operate in your universe as you knew it. For the people at the time, it worked, even though we know fundamentally at the heart of it, it was a wrong model. And it makes me wonder about us today, where we think we know because these things work, but who knows what comes down, 1,000, 2,000 years from now.
Well, Copernicus came up with the heliocentric solar system where the sun was the center, but he was criticized. He was criticized because his model didn't quite fit the data as well as the Ptolemaic model that you mentioned, because the Ptolemaic model had epicycles, circles inside circles inside circles. Now, with enough circles, I think you could probably fit the stock market with epicycles. With hundreds of epicycles, you could probably fit anything you want. Yesterday's stock exchange results, for example. So the epicycle model was good. It fit the data, but it was horrible. No one believed it was the ultimate theory, except the church maybe. But Copernicus said, no, the heliocentric model with the sun at the center is simple, elegant, and almost fits the data. What was missing is ellipses. Kepler, of course, showed that planets move in ellipses around the solar system, not in perfect circles. But I think the analogy is correct. Just because something works and is ugly does not necessarily mean it's true.
Yeah. But Einstein was missing a key force in his attempt to get to a theory of everything. Even if we feel that we're close to finally getting to this theory, I can't help but think about Ptolemy, about Einstein, in the sense of there may be a lot more out there we have just no idea about.
Well, there is something called the onion theory, which says that you peel the onion, you get layer upon layer upon layer. The deeper you go, and the onion goes on forever. Maybe, but we have to look at the data. We have particles today that obey laws. We can measure them. The standard model seems to fit until 2 weeks ago. And so we have to stick with what works. But now that what works seems to have a crack in it, then we're forced to go into these realms where pure mathematics is the only guide. So that's the way Newton did it. That's the way Einstein did it. They took a huge leap of logic. They created systems that could not be immediately tested. When they were tested, of course, it changed world history. But initially, they took a gamble. And I think that's what string theory is about. It is a gamble, but it's also like a chess game. We, after 2,000 years, have figured out how the pawns move, how the bishops move, and the knights move. One day, we will have the God equation and figure out all the rules of chess. Then maybe we'll become a grand master of chess. So some people ask me, Professor, if you find the theory of everything, are you going to be unemployed? Are you going to be out of a job? And the answer is no. Just because you know the rules of chess does not make you a grand master of chess. There are all sorts of strategies, all sorts of intricate pathways that you can explore in chess beyond the rules of chess. And maybe that's where things like life, love, emotions, self-conscious, self-awareness, maybe that's where it comes from. That these are emergent phenomena. That once you know the rules of chess, then you can work out the emergent phenomenon, things like love.
All these come back to the physical rules that govern the universe.
That's right. So we think that ultimately, once you know the rules of the game, once you know the rules of chess, then you can start to create strategies, new ways of using these rules to create higher forms. So in other words, you become a grand master of the universe.
Well, what does it mean to be a grand master of the universe? And what do you think it would mean to have a theory of everything?
Well, there is a point at which Einstein's equations totally collapse. That's the Planck energy. That's the energy of the Big Bang. That's the energy at the heart of a black hole. That is 10 to the 19 billion electron volts. That's the Planck energy. That's an energy that we, as Earthlings on the planet Earth, cannot muster maybe for thousands of years. But one day, perhaps we will be able to attain the Planck energy. The Planck energy is the energy at which holes in space emerge, wormholes, similar to what you see in Star Trek and in Star Wars, holes in the fabric of space and time. This is not for us, but it could be perhaps for an advanced civilization in space or maybe for our own future. So think about that for a moment. Einstein's equations make possible the idea that there could be gateways to other universes that maybe, just maybe, we will one day explore. If you saw the movie Interstellar with Matthew McConaughey, it ends on string theory. It ends on a four-dimensional tesseract. That was the final scene with Matthew McConaughey. He's floating in hyperspace. And what is he floating into? A wormhole. A wormhole that is part of string theory. So you see, string theory is even invading Hollywood now.
Have you thought? You must have. I'm sure you think about these things all the time. What would happen if some discovery were to come that would potentially challenge the ideas of string theory?
Well, that's called falsifiability. You want to make sure that your theory can be proven incorrect as well. Well, if we find these new particles from the Large Hadron Collider and Fermilab outside Chicago, if we find evidence of new particles and they don't match the predictions of string theory, then out the window it goes. No matter how beautiful theory, the ultimate test is experiment. So a theory of everything could become a theory of nothing. That's why we want to probe this new result, just 2 weeks old. New particles may be discovered, and these particles are not part of the standard model. That's what's generating so many excitement.
And the title of your book, The God Equation, is this to you God? And in that sense, do you believe in a God and that this is what it would be?
Well, Einstein was asked that question, and he said he didn't believe in a personal God that gives you a bicycle for Christmas, that smites the Philistines, that walks on water. He didn't believe in a personal God, but he believed in the God of order, simplicity, harmony, beauty. You know, it didn't have to be that way. The universe could have been ugly. It could have been chaotic. It could have consisted of just a mist of subatomic particles, no consciousness, no people, just nothing, just a cloud of particles. That's the way the universe might have been. But the universe is gorgeous, it's beautiful, elegant. On one sheet of paper, on just one sheet of paper, you can write the theory of almost everything, and it fits the data, the low energy data, not the high energy data. But the low energy data is our world, and it fits our world, and it didn't have to be that way. Simple, elegant. And that's why I think that you have to go beyond simply a personal God. Now, let me say one more thing. Galileo was asked questions like this, and Galileo said, the purpose of science is to determine how the heavens go. The purpose of religion is to determine how to go to heaven. So in other words, they're complementary. They're not in contradiction to each other. Science is about natural law. It's about how the heavens go. But religion is about ethics, how to be a good person, how to go to heaven. So if we keep these two separate, then there's no problem. The problem occurs when people who are religious begin to pontificate about natural law, or when scientists begin to pontificate about ethics. That's when we get into trouble. But as long as we keep them separate, they are complementary, I think.
Has our response in just living in over a year now in a pandemic, has it affected the way you see society and its relationship to science?
Well, in my books, I write that humanity faces three cosmic challenges that could literally wipe us off the earth. The first is nuclear warfare. The second is germ warfare, or bioengineered germs escaping from the laboratory. And the third is global warming. These are three existential problems that we have to face. And as we mature as a civilization, we're going to have to confront these things. We just can't bury our head in the sand and say, this is for future generations. This is for us. This is for our children, our grandchildren, to make sure that we can give to them a world as rich as the world that was given to us.
Michio Kaku is professor of physics at the City University of New York, co-founder of string field theory, and author of the book that we've been in conversation about called The God Equation, The Quest for a Theory of Everything. Should add, he's also host of a program that you hear on this radio network called Explorations, and he will be participating in an event this Friday with the San Francisco Commonwealth Club. If you're interested in viewing that event and participating yourself, just check out the San Francisco Commonwealth Club's website, where they have details of how to participate in Friday's event. Michio Kaku, I've enjoyed our conversation very much, and I thank you for doing this.
My pleasure.